What's up, bitches? If you have your thermodynamics exam and you're very worried, do not worry, because today I'm going to teach you guys how to pass. So, for your simple Brayton cycle, the most important thing is to know your TS diagram by heart, okay? In the meantime, I'll also explain how the Brayton cycle works, okay? So you have air that is at a certain temperature, at a certain entropy, okay? That's step one. The air is going to go into a compressor. The compressor is going to increase the temperature, but still keep the same entropy, ideally. So it's just going to go straight up like this, too. Next, this air is going to go into a combustion chamber. The combustion chamber is both going to increase the temperature and its entropy, 3. Okay. After step 3, it's going to enter a turbine, and the turbine is going to use this air to create power. So it's going to use its temperature. Okay. When it leaves, it's going to be at step 4 with less heat, but the same entropy. Then it goes into a heat exchanger and returns to step 1. Okay. And that's your simple Brayton cycle. Let me draw these arrows, okay? You don't necessarily need to know this step by heart, but you do have to know the TS diagrams to solve your problems. And this is what your professor is probably going to ask in your exam, okay? So you have to keep in mind from step 1 to 2, it's isentropic. Same thing with 3 to 4, isentropic. From step 4 to 1, it's constant pressure. Constant pressure. And same thing with 2 to 3, constant pressure. From step 2 to 3, you have heat that comes in, and 1 to 4, heat that comes out. From 3 to 4, you have work being produced by the system, and from 1 to 2, work being produced on the system. And that's it. If you have your notebook, or if you're allowed to have a cheat sheet, you should like copy exactly this over here. So let me just explain a little bit. What does isentropic reactions mean? It basically means that you can use these equations, okay? This should be in your formula sheet. We don't need these volumes over here. We're just going to use this equation over here, okay? This should usually be in your cheat sheet or your formula sheet. K minus 1 divided by K, okay? Since we're dealing with air, K, which is some random constant, it's going to be equal to 1.4. 1.4. Okay. So that's your isentropic formulas. You use this to find the pressure and temperature at point 2, like if you have all the information from point 1. The next formulas that you have to know is that Q in or Q out, it's the same thing. It's equal to the difference in enthalpy, okay? The difference in enthalpy is equal to Cp if you have constant pressure, or Cv, times the difference in temperature. Since our volume changes, we just ignore this. We're going to use this equation right here. That's it. Okay? Keep in mind that some questions, they're going to ask you the net work being done. That's equal to the heat that comes in minus the heat that comes out. If they ask your thermal efficiency, that's going to be equal to your work net divided by the heat that comes in. Okay? You have to know these 3 equations, okay? Sometimes the question is going to ask you for like capital Q, okay? What's the difference? Capital Q takes into account the mass, the amount of mass that's going into your system, delta H. Or what you're going to use is this, Cp delta T. Okay? Little q is just Cp times delta T. Okay? That's the only difference. And that's all you need to know for your exam. Now let's do an example together just so we can practice. Okay, so let's do this problem together. I'm not going to read it out loud, but I highlighted whatever is important. You have your minimum temperature, maximum temperature, blah, blah, blah. Okay. And I also included a question that has thermal efficient, compressors, isentropic efficiency, and turbines efficiency, just so like you guys could know what to do in these scenarios. Okay. The first thing that you do when you're dealing with a Brayton cycle question is you draw your TS diagram. Okay. Otherwise, you're going to get lost and you're going to look stupid in front of your prof. We're going to draw step 1, step 2, 3, 4. This is the first thing that you should do for any Brayton cycle problems, okay? Isen, Q in, Q out. All right. At point 1, you're going to have a certain pressure, certain temperature. Point 2, you're going to have another pressure and another temperature. Pressure 3, temperature 3. Actually, hold on. I'm going to write it over here just so it's clearer to see. Pressure 3, temperature 3, pressure 4, temperature 4. All right. The question is going to give us some clues, okay? Maximum temperature, minimum and maximum is 27 and 727, okay? Maximum temperature is right over here at 0.3. You see it's at the top. So that is 727 degrees Celsius, but we're going to work in Kelvin. So this is 1000 Kelvin, yeah. The minimum is at pressure 1 because that's where the minimum temperature is. And it's saying, what did it say? 27. So that's 273 plus 273. That is 300 Kelvin. Okay. Next. It's saying it's designed so that the maximum cycle pressure is 2000. And remember that from 2 to 3, it's going to be constant pressure. So we know that at point 2 and 3, the pressure is 2000 kPa. 2000 kPa. And the minimum is 100. So we know from point 1 to 4, it's constant pressure. So we already know these temperatures, pressures. Okay. Determine the net work. Net work equals to Q in minus Q out. So we have to find out the temperature at point 2 and point 4. And the rest is easy. We just have to follow the formulas, okay? So let's start. From point 1 to 2, it's isentropic. So, whoops. So you follow this. You just follow this equation right here. If my thing works. 2P. Hello? There you go. P1, sorry, P2 is here. K minus 1 over K, okay? So we know that T2 equals the T1 times the difference in pressure. So P2, we have 2K over here. Actually, I'm just going to write it down just so it's easier. K minus 1 is 1.4, negative 1 equals 0.4. So 0.4 over 1.4. T1 is equal to 300 Kelvin. P2, we have is 2000 kPa. 1000. And P1 is 100 kPa, right? Yeah, there you go. 100. 0.4, negative 1.4. If you plug it in this in your calculator, you should get something about 706.1 Kelvin. However, keep in mind that your turbine has an isentropic, your turbine and your compressor's isentropic efficiency is 80%. When you have an isentropic efficiency for your compressor, this line over here, it's ideally, so I'm just going to write an I. But realistically, in your problem, it's going to look something like this. Okay? Same thing with your turbine. Ideally, it's going to be 3 to 4 over here, a straight line. But if it has an efficiency, it's actually going to look something like this. That's going to be your actual 0.4. And this is for ideally. So what do you do in this case? You have your compressor's efficiency. It's equal. Well, okay, look, basically it's equal to the difference in your enthalpy, okay? But we know that enthalpy is equal to Cp delta T. Cp delta T. So these goes away. So you have your efficiency, which is equal to T2, ideally, negative T1. T1 is going to be the same. 2 negative T1. So T2 is equal to T1 plus compressor's efficiency times T2, ideally, negative T1. This is just basic algebra, okay? Once you plug in all of the numbers, this is 300 Kelvin plus 0.8, ideally whatever we find, 706.1, negative 1, negative 300. We get our actual T2, which is equal to about 807.6 Kelvin. If you get a temperature that's like smaller than the ideal temperature, it means you messed up one of the signs, like probably the denominators over here, okay? So just pay attention. So T2, we have 807.6 Kelvin. Now for T4, you do the exact same thing, okay? You have to use the isentropic formulas. T3 divided by T4 equals to P3 divided by P4, 0.4 over 1.4. So T4, this is just basic algebra. T3 times P3 over P4 minus 0.4 over 1.4. T3 was 1000 Kelvin. Pressure 3, we wrote it up here. It's 2000 kPa. P4, we have it over here. It's 100 kPa. Minus 0.4, 1.4. So T4, ideally, it's going to be about 424.9 Kelvin. Okay. So now, since our turbine also has an efficiency, we have to do the same principle. Okay. Ours has a efficiency of 90%. So T equals to the exact same thing. T3 minus T4. 3 minus T4. Okay. So to know if the ideal temperature is in the numerator or denominator, you just have to keep in mind this shape over here. You have to memorize it, okay? We know that ideally it wants to keep a straight line, like the same entropy. So the temperature is slightly gonna be lower. Ideally your temperature is gonna be slightly lower. So if it's slightly lower, well, you're subtracting it, so it's gonna be in the denominator, okay? That means T4 is equal to T3 minus turbine efficiency, T3 negative T4. We know T3 is 1000, 0.9, 1000, negative 4, damn, 424.9. Okay, so we get our actual T4 to be equal to 482.4 Kelvin. If you get an T4, your actual T4, that's less than your ideal T4, it means you fucked up with the numerator and denominators, okay? So just pay attention to that, but otherwise it's pretty simple. If you memorize this shape, the rest is just like common sense. 482.4 Kelvin. Now we have everything to find our what are we looking for? The net work, okay? So let's come over here. Q in equals, damn, it's not fucking working. Wait, what's it working? The cycle is at per unit mass. When it asks something like this, it's not asking for your Q, like small q in. It's asking for your capital Q in. But it's asking per unit mass. So this is going to be 1 kilogram per second. Okay. So 1 times Cp, 1.005 That's this, the CP for air, times Q in. You should memorize this. It's from 0.3 to 0.2. So T3 negative T2. T3 is 1,000. And T2, we found it to be, I think it was 800 something, right? Yeah, 807.6. 7.6. This should give you about, let me just calculate it, 193.4 kilojoules. Q out is equal to 1 kilograms per second times CP 0.005 times, and it's going to be from 0.4 to 0.1 Q out, as I drew over here. So 0.4 is 482.4 negative 300. That should give you about 183.3. So finally, whoops, what just happened? Whoa, 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 whoa. My bad, guys. Work. Hello? What the fuck's happening, bro? Damn. Work net equals to Q in negative Q out is equal to 193.4 negative 183.3. This gives you a value of 10.1 kilojoules. This is our final answer for our work net. And if you want to find the thermal efficiency, you do work net divided by Q in. 10.1 divided by Q in, 193.4. Gives you about 0.0522, which is equal to 5.22%. And that is how you solve your simple Brayton cycle problems. Thank you for watching.